Hello everyone, my name is Shichang Xin. Here's my seminar presentation. The topic is motion artifact removal and signal enhancement to achieve in vivo dynamic for field OCT. And my professor is Guo Wenjun Jiao. Okay, the outline consists of the first part, introduction, the second part, method, and the third part, result and conclusion, and finally, future work. Okay, in introduction section, first of all, what is dynamic FFOCT? In standard FFOCT, the interferometric amplitude is obtained by combination of images for which a modulation of the path difference is induced in the reference arm. In dynamic FFOCT, there is no reference modulation and only movements in the sample itself contribute to the signal modulation. And the motivation and purpose of this paper is present a filtering procedure based on singular value decomposition, which is SVD, to remove artifacts arising from sample motion during dynamic full-field OCT acquisitions. And in method section, the paper introduces a filtering process based on SVD to eliminate artifacts induced by sample motion during the acquisition of dynamic FFOCT data, including those caused by environmental noise from data obtained in clinical settings, including in vivo data. Furthermore, the paper proposed a novel approach based on accumulating and computing dynamic images, which leads to a higher signal-to-noise ratio (SNR), thereby enabling deeper tissue image for dynamic visualization. And picture A shows FFOCT setup in inverted configuration top view. And figure B shows schematic of the sample actual oscillations around the coherence value due to mechanical vibrations. And singular value decomposition is based on principal component analysis. And what is PCA? PCA finds a projection X in the feature space to represent a dataset when applied. Through PCA, two principal components can be extracted, represented by the two longer red lines in the diagram, with the longer red line being the major component with the larger variance. The variance of the largest principal component is 13.26, and the variance of the second largest principal component is 1.23. Different projection vectors represent different principal components. And here we reference another study that utilizes PCA analysis with two friends to provide an illustration. This analysis roughly separates into two principal components. PC1 represents static tissue signals, while PC2 represents blood flow signals. Next, let's discuss singular value decomposition. It's important to note that SVD can be applied to raw data without being restricted to square metrics. Through SVD, we can directly obtain eigenvalues and eigenvectors by subtracting the static tissue signals. We can isolate the vascular signals. These figures present various temporal eigenvectors and associated data used for artifact detection. Figure A shows first few temporal eigenvectors, and Figure B shows zero crossing rate computed for each temporal eigenvectors. And zero crossing rate is a numerical metric used to describe the rate of change of a signal. And Figure C shows absolute value of the derivative of the level crossing rate computed for each temporal eigenvector. In summary, these figures illustrate how temporal eigenvectors and related data are employed for the detection and removal of artifacts, thereby enhancing the quality and clarity of the images. Okay, there's result and conclusion section. In the result section, these figures display lung biopsy for cancer detection. Artifacts arise mainly from mechanical vibration and air conditioning. Figure A shows original dynamic FFOCT images computed on the row stack, and Figure B denoised images computed with SVD filtering. However, Figure C is sum of the spatial eigenvectors' absolute value removed by the SVD filtering, and red arrows are highlighting cells that were partially maxed by motion artifacts. Okay, and fibroblast image taken on the setup present Figure 1. Artifacts arise mainly from mechanical vibrations leading to fringes pattern. Red arrows are highlighting subcellular features. Only the bottom one was visible on the original image. These figures demonstrate how the SVD filtering method has successfully eliminated interference caused by mechanical vibrations, thereby enhancing the quality of dynamic FFOCT images and making cellular structures more easily distinguishable. This is particularly valuable for biological research. Okay, so this part is about extending penetration depth using non-stationaries. In addition to motion artifacts, a drawback of dynamic FFOCT compared to standard static FFOCT is the reduced penetration depth, due to the weak signal level produced by the sample fluctuations. In order to enhance the dynamic signal strength, and so improve penetration depth, they propose computation of the dynamic image from the cumulative sum of the signal, rather than the raw signal. So Figure A shows the maximum reached by the cumulative sum is 3 times higher with the bias. And the Figure B and C are dynamic image of a macaque perceptor layer using standard deviation, and a proposed method based on cumulative sum. So this result indicates that the proposed method significantly improves the SNR of dynamic FFOCT images, particularly when imaging deep within the tissue. Okay, in vivo mouse liver dynamic image taken on clinical setup with custom mount. Artifacts mainly arise from the breathing and heartbeat. And in Figure A, in vivo dynamic FFOCT image of a mouse liver computed on a row stack with a standard deviation. And Figure B is about the SVD denoised stack with the standard deviation. Figure C shows the SVD denoised stack with the cumulative sum. This result also indicates that the proposed SVD filtering and accumulation methods are effective in removing motion-induced interference in vivo dynamic image, thereby enhancing image quality and SNR. Okay, the conclusion section. The paper proposed a filtering algorithm based on the SVD to effectively remove motion artifacts from dynamic images, and this method was applied on an in vivo dataset and is promising as long as actual motion is smaller than the coherence value depth. And second one, the paper also proposed a method based on the cumulative sum to enhance non-stationarities, in temporal signals which led to an SNR factor increase of 1.9 on average for ex vivo samples and 3 on our in vivo dataset. These general techniques could be applied to any other imaging modality with sub-diffraction phase sensitivity. The final part, future work. I'm going to attempt to remove horizontal strip noise in the image while I'm using SVD algorithm, and I will try to improve SVD algorithm and combine the method based on the cumulative sum that I mentioned in this seminar presentation. And this is my references. That's my seminar presentation. Thank you for your listening.